All right, so as we start moving through this particular unit, what you're going to find is that we're going to start talking about polynomials that have a higher degree than a quadratic. So in the last video that you watched, we were looking at everything where the highest power was an x squared. And so we were looking at parabolas in every single one of those graphs. So in this lesson, we're actually going to start looking at graphs of polynomials that have highest exponent of things like a cube or a fourth degree or a fifth degree and so on. And so what we're going to talk about on this first and second page is what things am I going to look for so that I can figure out what the graph's going to look like. So the first thing we're going to talk about is this concept called end behavior. So what we find out about quadratics and other polynomials is that if there are any twists or bends in a polynomial, they happen in the middle of the graph. So as x gets really, really big, so as I go further and further out to the right, or I go further and further out to the left, the curve is always going to do one of two things. It's either going to shoot to the sky or it's going to fall to the floor. So we talk about our left side or our right side rising or falling as x gets very big or x gets very small. So the way you can kind of look at this particular function has an odd degree and its leading coefficient is positive. So this would be something like y equals 2x cubed plus 4. That is an odd degree and the leading coefficient is a positive 2. What's going to always happen on the ends of the function are the right-hand side is going to go to the sky, it's going to rise, and the left-hand side is going to fall to the floor, it's going to fall. That's true of any odd degree polynomial that has leading coefficient that's positive. If I change a little bit of gears and I use a negative leading coefficient, something like y equals negative 3x to the fifth power plus 4x minus 6. So really the most important parts of this are the fifth power because it's an odd degree and the fact that the leading coefficient is negative. In this regard, my left side now is the one that goes to the sky and the right side is the part that falls to the floor. So notice that these two graphs look very similar. This one, the right rises and the left falls, and this one, the left rises and the right falls. That's called end behavior. So not only can we talk about that in regards with odd degrees, we can also talk about it in regards with even degrees. So if I gave you an even degree polynomial, something like a quadratic or a quartic or a sixth degree and so on, what's going to happen with an even degree is that if I have an even and a positive leading coefficient, something like y equals 2x to the fourth plus 3x squared minus 5x, we'll say. The important things of this are the fact that the degree is even and the leading coefficient is a positive value. When those two things happen, both ends, both left and right side, go to the sky. That's true anytime that you have an even degree and a positive leading coefficient. If I switch gears, leave it an even degree, but I talk about a negative leading coefficient, something like y equals negative x to the sixth power plus 5x cubed minus 8. If I look at something like this one, I still have an even degree, but now my leading coefficient is negative. So in this regard, as we go off to the left and we go off to the right, those two sides now go down rather than going up. So the first thing that I'm going to ask you in all of these problems is to tell me what the end behavior looks like. So does the left side go up or down? Does the right side go up or down? That's all you're going to be asked to start the problems. And we can figure out those things just by looking at what's the highest power and then what's the leading coefficient. Beyond end behavior, the next thing we're going to talk about is it's going to be important that we can figure out what the zeros of the polynomial are. So in the last unit, we talked about zeros. We talked about the fact that those are the x-intercepts. So those are going to be important points on my graph because that's where my graph is going to hit the x-axis. Some things about the zeros of any polynomial. Number one, if you start with a polynomial that has an n degree, so something like x to the fourth plus 4x squared plus 6, that has the chance to hit the x-axis the same number of times as its degree. So it has the opportunity to hit the x-axis 4 separate times. It doesn't mean it has to hit 4 times, it just has the opportunity to hit that many times. The next thing is that when you look at a curve and it has all kinds of bends and twists in it, it can only have one less than the degree turns. So that's what I mean by n minus 1 turning points. So if I'm going to use this same example, not only would I have the opportunity to hit the x-axis 4 times, but I would also have the opportunity to have 3 different turning points. So something like that. Notice that this graph that I just drew hits the x-axis 4 times, and then I've got 1, 2, 3 different places where I go from decrease to increase and vice versa. So that's what I mean by turning points. If you have a 0 that repeats itself, sometimes that happens. You have a situation where the curve is going to bounce off the x-axis. So what would that look like? If I drew a graph again, if I had something that looked like this, it hits the x-axis in 2 places. Notice here it passes through the x-axis, and here it bounces off the x-axis. These 2 things happen when you have in what's called an odd multiplicity. And this one happens when there's an even multiplicity. So that means that a 0 repeats itself twice, you're going to bounce at that point. If a 0 repeats itself 4 times, you're going to bounce at that point. If a 0 repeats itself 3 times, or once, or 5 times, you're going to pass through the x-axis at that point. That's called multiplicity. So what rules are we going to follow? That's a whole lot of terminology and a lot of different specific things. So what are we actually going to do? First thing, you're going to tell me what the end behavior is. Second thing, you're going to find the zeros. Third thing, you're going to plot every single value between the zeros. So we'll talk about what I mean specifically about that when we do a couple of problems. After that, you're going to sketch the graph. So I've got a couple of problems that we're going to do together. So the first one looks like this. So take a second and write that down. And then we're going to talk about what happens. So the first thing that we're going to determine is what's the end behavior. So I'm going to label that as EB. Since we have an odd degree, that means that one side of my curve is going to go to the sky and one side of my curve is going to go to the floor. So if I want to determine which one of those things it is, I have to go back to my little chart that I had, and we're going to see that if I have an odd degree with a positive coefficient, we fall on the left and rise on the right. This one, however, has a negative leading coefficient, so this one is actually going to rise on the left and fall on the right. So how do I usually write this? I usually write it like this. We're going to go up on the left and down on the right. That's all you need to show me for end behavior. We're going to rise on the left and we're going to fall on the right. The next thing you're going to do is find the zeros of the function. So I'm going to take this and set it equal to 0, and we're going to use some of our methods in order to solve the equation. So the first thing that I would notice about this is that the leading coefficient is negative. So rather than try to factor this with a leading coefficient that's negative, let's take a negative out of everything and see if it's maybe a little bit easier to factor. So I'm going to take a negative out of all of this. Now, when you take a negative out, all it does is change all of the signs. And remember, since I put this equal to 0, I don't even need to show that I took a number out. That's true anytime you're equal to 0. So now my job is to factor. And we learned in the first unit that anytime you see 3 terms, you should try and factor using a concept called grouping. So we're going to group the first 2 terms together and figure out what's in common. There's an x squared in common. What's left in those 2 terms would be an x minus 1. Second 2 terms, I'm going to take a negative 4 out. And what would be left in those two terms is an x minus 1. So once we've broken those groupings apart, now we can rewrite these as x minus 1 once and x squared minus 4 in its own parenthesis also. Now in this particular case, you can continue to factor. This is plus 2 and minus 2. Which means that this particular graph is going to hit the x-axis in 3 places. Those 3 places being 1, positive 2, and negative 2. So on my graph, all I'm going to do is go to those points and put dots on the x-axis. Positive 1, positive 2, negative 2. Then I'm going to realize what we said about end behavior. End behavior is up on the left and down on the right. So all I'm going to do is show that. The right-hand side is going to go to the ground, and the left-hand side is going to rise to the sky. My job is to figure out what on earth does this look like in between the end behavior. And all we're going to do is make a t-chart. The t-chart that we're going to use is going to be every single x value between the zeros. So when I make my t-chart, what values do I pick? Well, I had a 0 at negative 2. So I'm going to plot negative 1, 0. I have a 0 at 1. I have to plot in between 1 and 2. So I'm going to plot 1.5. And all we're going to do is do evaluation. We're going to take those numbers from my t-chart and we're going to plug them into the calculator and see what we get. Always in the original equation. So the first one, if I put in negative 1, we're going to do negative 1 cubed plus negative 1 squared plus 4 times negative 1 minus 4. And that's going to give me a y value of negative 6. If I plug in 0, 0 is an easy evaluation. 0 plus 0 plus 0 minus 4. And then we're going to do an evaluation the same way, but with 1.5. So we'll do negative and then 1.5 cubed plus 1.5 squared plus 4 times 1.5 minus 4. And I get 0.875. So about 0.9. So I'm going to take those points, we're going to plot them, and we're going to see what it looks like. So the first one to plot was at negative 1, negative 6. So we're down here. Then we're up at 0, negative 4, which would be here. And then we're a little bit above the x-axis at about 0.9. So a little bit above in those two dots. And all I'm going to do is connect the dots. And there's what my curve looks like. The last thing I'm going to tell you to do on every problem, domain and range. Anytime we graph a polynomial, we're talking about all real numbers as the domain. Anytime we graph a polynomial, it depends on what the polynomial looks like when we determine the range. Now notice the left-hand side of this goes to the sky. The right-hand side goes to the floor, which means that this is never going to stop going up or down. So that's why the range is also all real numbers. The next problem is going to be similarly done, but it's going to look different because it's an even degree. So take a second and write down that, and then we'll talk about what on earth are we going to do. Now, the first thing you should notice is that this is an even degree, so I want to determine end behavior. The nice thing about even degrees, either both ends go up or both ends go down. So once I figure out which one it is, they both do the same thing. Since my leading coefficient is positive, we go back to our trusty little guide here. If my leading coefficient is positive, we've got either this graph or this graph. Since my leading coefficient is positive, that means that both ends are going to go in the upward direction. So I'm going to write both ends up. Next thing you want to do, find the zeros. Okay, now the first thing that you learned, or one of the first things you learned when we started the prerequisites unit was how to factor correctly. Now factoring, the first step always is to take out a common factor if there is one. Now if you look at all four of those terms, you have an x in common, so you can take an x out right away. So that's going to be the first thing I do, take an x out. That reduces all of the powers by 1. And what that means is, if you ever take out a variable, we learned that one of your solutions, one of your zeros, is 0. So we're going to pass right through the origin for this particular function. Then we're also going to talk about how to figure out the rest of this. Again, notice that the rest of this has 4 terms. So we're going to factor this by grouping just like we did in the first problem. So I'm going to look at the first 2 terms and realize that there's an x squared in common. So I get x plus 5 left over. Going to look at the second 2 terms and realize there's a negative 4 in common. So I can take out and have an x plus 5 left over. Remembering that if I take a negative out, this sign also changes. That's why it changes into a plus 5. That plus 5 gets written once. And then the x squared and minus 4 go in a parenthesis together. You can factor one more time then. That's a difference of squares. So x plus 5, x plus 2, x minus 2. So this is going to have 3 more places that it hits the x-axis. Those places would be negative 5 and plus and minus 2. So we're going to put all of those dots on the graph. Now there are 4 places that this is going to hit the x-axis. They would be at negative 5, negative 2, 0, and positive 2. End behavior, we said both ends go up. So we're going to show that. Up on the left, up on the right. Now I'm going to plot and make a t-chart to figure out what extra values are going to help me graph the function. Now again, you want to plot every whole number or integer value between the zeros. So I have a 0 at negative 5, which means I want to plot negative 4, negative 3, 0 at negative 2, so I want to plot negative 1, 0 at 0, so I want to plot 1, and my last 0 is at positive 2. I don't need to plot anything outside of the zeros because I already know what's going to happen. The right side's going to shoot up and the left side's going to shoot up. That's called end behavior. So we're going to take those values and plug them into the calculator. And again, we're going to use the original function while doing that. So don't ever use a function that you've manipulated. Always go back to the original when you're plotting points. So the first one I'm going to plot is going to be at negative 4. Remembering that I'm going to put the negative 4 in parentheses every time. Negative 4 to the 4th power plus 5 times negative 4 to the 3rd power minus 4 times negative 4 to the 2nd power minus 20 times negative 4. And I get a negative 48. So a big number, which is fine. That's okay. The next thing we're going to do is then plot negative 3 the same way. So we're going to do negative 3 to the 4th power. Then we're going to add on 5 times negative 3 cubed minus 4 times negative 3 squared minus 20 times negative 3. And I get negative 30 as my answer. Next one we're going to do then is negative 1 and then 1. So you can do your evaluations along with me. I get positive 16. And then if we plot 1, and I'm not going to put the 1 in parentheses because it's not needed since it's a positive number. Oh, 16 is wrong. I did the last one wrong because I forgot to put the 5 in there. That should be 5 times negative 1 cubed. So let me insert that. That's supposed to be 12, not 16. I apologize. Okay, so let's make sure I type this one in correctly. 1 to the 4th plus 5 times 1 cubed minus 4 times 1 squared minus 20 times 1. And I get negative 18. So what we're going to want to do is plot these points. Now, it probably would be smart of us to scale our graph in some way. I'm going to scale my graph, we'll say, by 4s. So I'm going to say that every dash is actually 4. So when I plot negative 48, I'm going down by 12 spaces. So I'm going to be, that's 10, 11, 12. We'll say we'll be about there. Negative 30 is going to be down about 7.5 spaces. 1, 2, 3, 4, 5, 6, 7, and about a half. 12 would be up 1, 2, 3 spaces. And then negative 18 would be down 1, 2, 3, 4 and a half spaces. So if I connect those dots, we dip way down, then we dip up, we come back down, and we finish. And so we've got a graph that looks something like that with all of those points plotted. Now, do you have to scale by 4? Could you have scaled by 5 or by 6 if you wanted to? 6 would have worked very well, actually. Actually, now that I think about it, I probably should have scaled by 6 instead of 4. So the last thing that you would want to do here is domain and range. Again, polynomial, we know the domain, all real numbers. The range, you're looking high to low. So what's the lowest value that this approaches? The lowest value this approaches is down way here at negative 48, and then it goes to the sky from there. So from negative 48 to infinity. You can kind of make note that if you have an even degree, your range is going to be cut off. If you have an odd degree, like the first one, your range is going to be all real numbers. Okay, that's a rule of thumb that you can write down and make note of. I've got 2 more problems that I want you to try. I'm going to have you try them on your own before you come to class. And then we will discuss, I'll show you what the pictures look like just like I did with the parabolas, and we'll discuss any issues that you might have with these. So copy those 2 down, and I'd like you to graph those on your own, and then we'll talk about issues when you come to class on Monday.